Hello, everyone. Welcome to another session of the Porous Media Tea Time Talk. My name is Marcel Moura, and I'm joined here on the studio by my friend Mohammed Nouripour. We're both from the University of Oslo, and today it's the session number 56, so we're very happy about it. And we are part of the Interpor Young Academy. So today we are welcoming here Tomás Aquino from Spain and Wenhai Lei working in Sweden. And we're going to start straight away with the presentation by Tomás Aquino. So I'm going to bring you up on the stage like that. And Tomás Aquino, he is from the Institute of Environmental Assessment and Water Research in Spain. And he obtained his PhD from the University of Notre Dame, Indiana, USA in 2016. And after studying for his undergraduate and master's degree in physics at the University of Lisbon in Portugal. Before starting his current position as a permanent researcher at the IDAEA in 2022, he was a postdoctoral researcher at the same institution from 2016 to 2019, and a Marie Curie individual fellow at the University of Rennes in France from 2019 to 2022. So today, Tomás is going to talk to us about interface shear, how interface shear controls surface reaction, efficiency, and chaotic flow through porous media. So before I give the floor to Tomás, I just want to remind everyone that you can write your questions anytime in the comment section, and then at the end of the talk, we'll bring them up, we'll read them to Tomás. So Tomás, you don't need to monitor the comment section because we will just read the questions to you, okay?
Okay, great.
So please, whenever you're ready, the floor is yours.
All right, so hello everyone. Thanks for being here. Thanks also for the invitation to the organizers and for the introduction, Marcel. So today I want to tell you a bit about how chaotic advection impacts fluid-solid reaction in porous media. And so the first question is, what is chaotic advection? So the key characteristic of chaotic advection is the exponential divergence of nearby trajectories as a tracer gets advected by the flow. So this exponential divergence leads to efficient exploration of space, and this in turn leads to efficient mixing called chaotic mixing. So this is quite well known in the context of turbulent flows, but more recently it has also been experimentally observed under steady laminar flow through 3D porous media. Right. So the thing is that the mechanism that leads to this kind of dynamics is actually quite parsimonious. So there is reason now to believe that this might be the norm rather than the exception when we're talking about 3D as opposed to 2D porous media. Right. So now the basic mechanism that leads to this kind of dynamics is that if you imagine a material line of an advected tracer going through this flow, as it goes through the porous network and as it diverges and remerges across these divergences and remergings of pore throats, it gets folded and it gets stretched, and this leads to the kind of exponential behavior that I was talking about before. Now, a key ingredient here is that the pore throats and the trajectories can reorient as you go through the network, which is something that you don't have in 2D and which is essential to get this kind of net stretching effect that then leads to this chaotic mixing. Now, this type of dynamics is actually analogous to one of these sort of quintessential chaotic mixing maps called the Baker's map, which is schematized down here. And this is basically just a way of representing what a baker does as they stretch and fold the dough to get it to mix efficiently. Right, so again, our goal was to look into the effect of this kind of efficient mixing dynamics on fluid-solid reactions. So we looked at a simple fluid-solid reaction setup. We just have a single dissolved species in the fluid phase, which can react at a constant rate, but only when it comes into contact with the solid, so at the fluid-solid interface. As the underlying medium, we picked a body-centered cubic bead pack, which is a kind of crystalline structure that you see represented here. And the reason we chose this kind of crystalline structure is that by just fixing the orientation of the flow with respect to the structure, so with respect to the packing symmetries, we can control how much chaos, how much chaotic mixing, how much chaotic advection we get in the flow. So, for example, if you take the flow to be oriented along the packing symmetries of the structure, you get no chaos at all, very irregular streamlines, like down here. But if you take certain flow orientations, you can get a bit of chaotic mixing or a lot of chaotic mixing. Right? So, as our metric to study the impact of this kind of mixing by the flow on reaction, we chose to look at something we call reaction efficiency at late times. And this is nothing more than the ratio of the effective reaction rate across the whole plume and the reaction rate that you get under well-mixed conditions. So if the plume was completely well-mixed in the pore space, in the fluid. Right, so here I'm showing you some numerical results for this quantity at a high dump color number of 100 in this case. So when you look at a low dump color number, which means slow reaction compared to diffusion, you basically don't get any effect of the mixing dynamics of the transport, because just diffusion on its own is enough to maintain the pore space mixed. On the other hand, for this kind of high or fast reaction rate, high dump color, you do get these regions near the grain where you deplete substantially, and this leads to incomplete mixing effects, which decrease the reaction efficiency, so the reaction compared to well-mixed conditions. Now, if you take a non-chaotic case, as I was discussing before, that's the black line down here, and you can see that there is virtually no effect of the flow. So as you increase the Peckley number, so the flow rate versus diffusion, let's say, you more or less maintain the same reaction efficiency. And this is just because, since the streamlines in this case are so regular, they don't really help you much in coming closer to the grain, right, to react. On the other hand, if you take orientations for which the flow is fully chaotic, which are the colored lines and the colored symbols here, you do get a significant effect at high Peckley number. But the thing is, and this we were quite surprised by, we didn't expect it, that this increase in reaction efficiency doesn't depend on the details of the flow, of the chaotic flow, as long as it is fully chaotic. So what I mean is that in particular, it doesn't depend on the Lyapunov exponent, which just measures how fast these trajectories diverge. So to understand this, we wanted to model this phenomenon so we know what's causing it and so that we can predict it. And for this, we built on a theoretical framework, which we call the chemical continuous time random walk, which essentially just takes into account the impact of reaction delays in determining the reaction rates. And in this case of fluid-solid reaction, the reaction delays, they come from the time that it takes for the solid to reach the reactive interface, and then also eventually to come back until the reaction actually happens, depending on the actual reaction. So using this theory, we can develop an analytical expression for this reaction efficiency at late times, which depends, or which is given in terms of a number of non-dimensionalized quantities. In particular, the dump color number that I already mentioned, the amount of available surface area, the mean first passage time of these excursions of solid to the surface, here non-dimensionalized by the diffusion time, and also a non-dimensional version, let's say, of the second moment of these first passage times, which basically encodes variability in these excursion times. So what this means is that to understand the reaction efficiency, we can now think in terms of understanding how these first passage times, these excursion times behave. So again, our original idea here was that since the mixing dynamics in the BCC, as I mentioned before, are analogous to what happens in the simple Baker's map, remember the stretching and folding map, we thought that first passage times to the walls in this map and in the BCC would behave at least qualitatively similarly. But turns out we were wrong. So it was for us quite a surprise to find that the dynamics are very different between the two. So what we see here on the plot on the left is the mean first passage time of the solid to the solid surface, non-dimensionalized by the diffusive one, so the mean time that you get without flow. So you see that for the BCC, as expected, if the flow is non-chaotic, this stays more or less constant. It's diffusion doing the job. But if we take the chaotic cases, again, they behave similarly, but you do get a decrease in these mean first passage times. But as I was saying, the behavior of this decrease, even qualitatively, is very different from what we find for the Baker's map. So to understand this, we modeled these first passage times in terms of something called a restart process. So a stochastic process under restart is just some stochastic process, in this case, first passage times to the interface, subject to restart according to some rule, which in this case happens at a constant rate. And the idea here is that, so if we look at these Poincaré sections, which basically show you how solid or tracer trajectories intersect cross sections along the BCC in this case, we see that, as expected, if the flow is non-chaotic, the distance to the solid surfaces, represented here by colors, remains more or less constant as we go through the domain. On the other hand, when we look at chaotic orientations, we get this very efficient mixing across the cross-section. So our idea was to say, well, let's think of these first passage times, or the first passage time process, as a first passage time under pure diffusion, but subject to restart at a constant rate at any random position inside the pore space to represent this efficient chaotic mixing of trajectories. So there is theory for this type of process. So we can relate these moments, these statistics, let's say, of first passage times to the diffusive first passage time, so without flow again, and a restart rate that we must now model and relate to the flow. Now, so in modeling this restart rate is when the difference between the BCC and the Baker's map becomes clear. And the reason, turns out, has to do with boundary conditions. Right? So here I'm mentioning restart times, which are just the inverse of the restart rates, normalized by the diffusion time. And so the idea is that in the Baker's map, we have essentially slip boundaries. And this is just because the deformation in the map doesn't really care about the boundaries being present. It's not hampered by the boundaries. So what we get is that the restart rate is proportional to the mean velocity, and so the restart time over the diffusion time just scales as 1/π. On the other hand, when we look at the BCC, we get a completely different behavior. And the idea here is that, so the reaction process happens at the interface between the fluid and the solid. And so the dynamics are controlled by the particles that get restarted here close to the solid surface, so that they can reach the boundary before they get restarted again. So if we look at a balance of diffusion and advection in this region, we find that the restart time, which is controlled by the low velocities here in the shear layer near the solid surfaces because of the no-slip conditions, now scales especially to the -2/3 when normalized by the diffusion time. And the Peckley number here is multiplied by an average shear rate, which is just the average shear rate near the solid surface. This L parallel here just gives you the typical length of these trajectories near the rates. Right? So using the restart theory again, we conclude that the mean first passage times in particular should scale as square root of the restart time. And this captures the behavior, the qualitative behavior at high Peckley quite well. And in particular, it explains this difference between the BCC and the Baker's map. Now, this theory can not only do the large Peckley asymptotics, let's say, it can also do the full regime of Peckley and Dunn-Cohen numbers. So for the first passage times, we can capture with the theory, which is here represented by the solid lines, the mean and second moments that we need for the reaction efficiency very well, and these symbols are determined by simulations. So you see that we get this transition between a diffusion limited regime at low Peclet and the shear limited regime due to the mechanism I just mentioned at high Peclet. When we then use this information using our chemical continuous time random walk description of reaction efficiency, we find again a very good match of theory and numerical simulations. And in particular, remember that when we have low damp color number, we have essentially no effect because the pore space stays mixed by diffusion anyway. But when you have high damp color number, so fast reaction compared to diffusion, we can get at high Peclet quite significant effect in terms of the reaction efficiency. So with that, to summarize, I've discussed how pore scale transport controls fluid-solid reaction rates when the reaction kinetics are fast. I've shown you how we can use a stochastic model of reaction delay to predict these reaction rates without actually resolving all the spatial complexity in the plume and the medium. And finally, I've discussed how we can put together this restart model that helps us explain and quantify how chaotic mixing controls reaction rates through the interface shear and not through the details of the chaos because of the boundary conditions in porous media. So before I finish, let me just quickly acknowledge my co-authors at least in the three main publications that I've been discussing here today. And with that, thank you very much for your attention. Thank you.
Good. Thank you, Tomás. Super nice. I welcome anyone to write the questions on the comments. But in the meantime, I have one quick question. So, how does the permeability affect the picture here? Like, for instance, how does the first passage time is affected by the permeability? I saw that you had like a psi as a function of kr in some of the equations, but
no. So this is, sorry if I went a bit too fast. So what the psi means is a first passage time density, a probability density function. So here we're just thinking of the relation between these excursion times and these delays to reaction. So because we are looking at the detail of surface reactions, at this point we're looking at the pore scale. So at the pore scale directly, there is no concept of permeability. No? So we're working directly with the velocity field. But now you're getting me thinking, if we have a system that we want to characterize at the Darcy scale, taking into account what's going on at the pore scale, how would it correlate? I don't know the answer off the top of my head. So I can think of two things. First, the permeability is somehow correlated with the Peclet number. So in regions of high permeability, you should expect generally larger velocities. But on the other hand, permeability typically correlates with porosity a lot. And porosity, I would expect to correlate with available surface area. Right? So I don't have a definitive answer right now, but what I'm thinking is that these are the two main contributors that will determine what will happen. But that's a good thing to think about.
All right. Super. Do we have any other questions from the studio?
Yes, I would like to ask a question about the reactions. And do you see if we can, one of the open questions in the reactive transport community is upscaling reactivity and reaction processes across different scales. Do you see, using your methodology, can we simplify this task, at least for simplified problems or simplified physics, and then for complex problems, of course, we can build on that. But what's your initial school of thought, how we can approach the problem?
Yeah, thanks for the question. That's great. So motivation for me for doing this kind of work is really to upscale. And so the idea behind this kind of description is to say, if we know certain statistical properties of the pore space and of the velocity field, we can say something about the reaction rates across a plume over those scales without having to know where everything exactly is. So this is the main idea here. So it turns out that, at least according to this description, we need first passage times, and the first passage times are somehow related to quantities like the amount of available surface area, and in more detail also to the geometry. But the idea is that just from these relatively simple statistical properties, that we can make these larger scale predictions without all the detail. Now, it's like you said, sometimes you need to simplify, at least to start. So here, it's important to recognize that for the very analytical results that we can get in this case, we are at the moment at least limited to a very simple chemical setup. No, so at the boundary we have just first order reaction. So one of the things I'm really interested in trying to do is generalizing these kinds of theoretical approaches to deal with nonlinear kinetics and with the reaction networks. I have not done that for the moment for the theoretical part, but I've been recently working on Lagrangian simulation tools for these kinds of surface reactions. And so I'm hoping to use this kind of Lagrangian picture, because it gives us direct access to the statistics, to try to see how we can relax the assumptions that we need so far for this kind of thing.
Excellent. Thank you very much.
Thank you.
Okay, now if we don't have any more questions from the audience, we can switch on to our next speaker. Our second speaker of today is Wenhai Lei. He is a postdoctoral researcher at KTH Royal Institute of Technology in Sweden under the supervision of Professor Sherwin Bagheri. Wenhai received his PhD in engineering mechanics from Tsinghua University in China in 2022. His research interest is mainly focused on multiphase flow in porous media, where he has published more than 10 peer-reviewed journal papers in multidisciplinary journals and high-impact publications, in addition to several patents in US and China. Thank you, Wenhai, for joining us today, and the floor is yours. But before going any further, we would like to see your presentation first so we can share it with the audience.
Hello. Whether I can start now?
Yes, you can start now, and we can see your presentation.
Okay. Hello, everyone. Good afternoon. I'm Wenhai from KTH in Sweden. Today, I'm very happy to give a presentation about triggering interfacial instabilities during force imbibition in depth variable microfluidic postmedia. This topic is also a part of my PhD study in Tsinghua University. So let's introduce the background. Actually, multiphase flow occurs ubiquitously in natural and industrial processes, such as in geological systems, chemical engineering, and biological systems. Today's topic mainly focuses on the background of geological system. For example, let's consider a rock. The rock geometry is very complex. When we want to conduct like CCUS or enhanced oil recovery, we should inject different fluid into such complex spaces. So the understanding of multiphase flow in postmedia is very important, which is a benefit for displacement operation for optimal trapping or displacement efficiency. Compared with traditional core flooding experiments, core flooding experiments just like a black box. It's really hard for us to see the inside fluid flow field. So microfluidics or micromodel provide a convenient or alternative methods to observe the multiphase flow in postmedia. And we can also make the multi-scale design from single pore scale to red-1 chip scale. It's controllable and repeatable. It's also have low cost and can achieve the faster test. However, for rock, it's a 3D pulse media. When we use the 2D microfluidic pulse media, how to make sure the realistic geometric confinement in the microfluidic chip is really a big challenge. By the way, the imbibition mechanism is different for these two systems. For example, for core scale study, when we use the core flooding experiments, the non-monodic viability effects is very obvious. Namely, when we use the stronger water-wide condition, we will get the lower displacement efficiency. However, for the pore scale studies, for example, we use the microfluidic experiments or 2D simulations. It usually presents a monotonic viability effects, which means the lower contact angle will always get the higher displacement efficiency. So it always result in complete imbibition patterns. So the incomplete imbibition patterns are hard to occur on the microfluidic chips or 2D simulations. So in this study, we want to mimic the 3D confinement in the microfluidic system. So firstly, introduce our previous work about the design of reservoir chip. First, we get a sandstone and then use a CT to scan and get the pore size distribution and the hierarchical pore geometry features. We will input this important statistical information into the random generation algorithm and then generate a similar microfluidic pulse media. We want to explore the new mechanism or new model, which can be upscaled by the direct numerical simulation or pore network model. We hope it can be combined with core flooding experiments to guide the field test. When we get a similar 2D pore size distribution, which present a similar pore size distribution as a real rock, as shown in this figure, it's a heterogeneous pulse media. But when we want to fabricate a uniform depth microfluidic chips, the uniform depth confinement will comprise such pore size distribution to a narrow area, which present a homogeneous 3D pore size distribution. But when we increase the depth variation in the microfluidic chips, the pore size distribution can be wider and wider. So the increasing depth variation can release the hydraulic diameter limitation gradually. So in this study, we will choose the optimal sequential photolithography and the multi-etching process to realize the 3D effect in the microfluidic chips. So first, we will choose. Use a random generation algorithm to generate a similar 2D pulse media, and then use a maximal ball algorithm to characterize the pore size in 2D pulse media, and separate the pores into the smaller pores, middle pores, and the larger pores. For the first etching, we will etch in all the pores, so we can get this microfluidic pulse media. And for the second etching, we will just etch in the middle and the larger pores, so we let the middle pores be deeper. And for the third etching, we just etch in the larger pores. Therefore, we achieve the depth variation in the microfluidic pulse media, where the larger pores contains the deeper depths. Here we define the depth variation factors as the ratio of the maximal depth to the minimum depth. So the larger depth variation factors can lead to the smaller geometric confinement. Based on above microfluidic system, we will conduct force imbibition experiments on such microfluidic pulse media. So let's introduce our microfluidic platform. It includes the power source, and we will use a microscope to observe the multiphase flow in the microfluidic pulse media, and then use a computer to calculate and quantify the multiphase flow in porous media. So this is our experimental results. The black color is the water, and the green color is the solid, and the yellow color is the air. This experimental results is a phase diagram which is controlled by the capillary number and the geometric confinement or the depth variation. When we decrease the capillary number and increase the depth variation, we can find it present incomplete displacement patterns, which is controlled by the color flow or film flow. However, when we decrease the depth variation to a uniform depth microfluidic chips and increase the capillary number, you can see it present a complete displacement pattern, which is controlled by the mean meniscus flow. So we will use the image analysis to quantify this flow behavior. So for the macroscopic porous media, we will calculate the water saturation and calculate the topology, for example, the Euler number of the water ganglia. And for the local flow behavior, we will use a slow algorithm to separate the porous media into several pores and to calculate each pore average saturation of the water. For example, in this phase diagram, we can reproduce a phase diagram. And the the color in the local pores represent, if it's black, means it's meaning controlled by the water film. And if the water saturation in the local pores is 1, which means it's controlled by the mean meniscus flow, which is fully saturated by the water. And here we introduce a new concept of the macroscopic capillary number, which is defined by the balance of viscous force and capillary force. So we can get that the critical capillary number equals 1. When we choose a weak geometric criteria microfluidic porous media, for example, alpha equals 3, we found that the critical macroscopic capillary number can be equals 1 can be used to separate the complete displacement and the incomplete displacement. Therefore, we get the critical Euler number and the water saturation, which is shown in as the green area in this figure. This green area can be used to separate this phase diagram as the complete displacement and the incomplete displacement. After the macroscopic flow patterns analyzed, we will go downscale to analyze the pore scale interfacial instability. So first, let's consider imbibition behavior in a square capillary tube. We will calculate the flow rate ratio of the color flow and the mean meniscus flow. When they are equals, we will get the critical capillary number. When the capillary number is smaller than the critical capillary number, which means the color flow will dominate the flow behavior. Otherwise, the mean meniscus flow will dominate the behavior. When the color flow dominates the flow behavior, the geometric criteria is also very important for the slab. Here, we should make sure that the mean meniscus at the pores of the capillary number of the mean meniscus at the pores should be larger than the capillary force of the color flow at the throats. So we can get the geometric criteria, which can be described by the depth variation, aspect ratio of throat and the pores. So we will use a direct numerical simulation and microfluidic experiments to validate these two conditions. So first, for the critical capillary number, we conduct a serial simulation and found if the capillary number is smaller than the critical value, it's dominated by the color flow. Otherwise, when the capillary number is larger than the critical value, mean meniscus will dominate the flow behavior and present stable cases. And for the geometric criteria, we can join its 3D surface in the space of depth variation, aspect ratio of throat, and aspect ratio of pores. And if you when we choose different depth variation varying from 3 to 1, you can get 3 different depth phase diagram, and each phase diagram have been validated by the numerical simulation data and the experimental results. Based on the critical geometric criteria, we can get some interesting phenomena. For example, let's see the phase diagram variation when we change the depth variation. You can see that the slab of area be larger and larger, which means if you choose a 3D postmedia, the slab will occur frequently and easier than the uniform depth microfluidic chips. And for the uniform microfluidic chips, you can also get some interesting phenomena, which is very useful for us to judge some experimental results in the previous work, who usually use the uniform depth microfluidic chips. For example, if you use glass to fabricate microfluidic chips, you will use HF etching, which will always produce the larger aspect ratio, as shown in this area. So the slab won't happen in the glass microfluidic chip. And if you use the silicon microfluidic chip or use the PDMS, it's shown in these figures. So the slab is also very difficult, as shown in this green area. After the pore scale interfacial instability analysis, we want to upscale this pore scale interfacial phenomena to the macroscopic patterns. So first, we input the critical capillary number and the geometric criteria into the improved dynamic pore network model. We will use the improved dynamic pore network model to reproduce such phase diagram, which fit well with our previous microfluidic experiments. And go ahead, we want to propose a simple theoretical analysis just to judge each pores. So we will use a slow algorithm to separate the postmedia into each pores, and then to check each pores whether its local pore geometry meet with the geometric criteria, and whether the flow condition meet well with the critical capillary number. If both conditions are satisfied, we think these pores will in this pore the slab will occur. And by the way, we can also calculate the slab of events frequency of the slab of events in the experiments based on calculate the water ganglia in the postmedia. This is the results. So let's compare the theoretical analysis and the experimental results. The color gradient are got from the theoretical analysis. The red color means the slab of events will occur frequently and results in the incomplete displacement pattern. And the blue color means the slab won't happen and present the complete displacement pattern. And all the results are fit well with our experimental data. So the frequency of the slab of events 50% can be used to separate complete and incomplete imbibition patterns. So let's give a conclusion. Our study proposed that 3D effect has been ignored in the traditional microfluidic experiments, while the flow mechanism in 2D and 3D postmedia are different. Our study opened a door to control the multiphase flow in microfluidic postmedia by considering depth direction design. And the emergence of complete or incomplete patterns is controlled by the geometric confinement of postmedia and the capillary number. Pore scale inversion mechanism is controlled by the slab of events, and the macroscopic imbibition patterns can be upscaled by the improved dynamic pore network model or the theoretical analysis. For more detailed information, you can refer our recent paper. Thank you. That's all.
Thank you, Wenhai. Thank you for this very interesting talk. I certainly enjoyed it a lot. So I will open up for the questions. And first, we have one question from the audience. I will start with that one, and then we go ahead from the questions if we have more from the audience or from the studio. The first one is from Tanki Zhu. What method did you use to etch the porous media Is it acid etching, or is it any other method?
Oh, okay. Actually, here we use silicon micro materials because our post media is very complex, so we must choose silicon. And for the silicon micro materials, here we use the DRIE and repeat the etching for 3 times. Actually, you can repeat more, but more etching times more expensive, so we just choose the 3 times. I think is enough.
Yeah.
DRIE.
I have 2 questions. The first
Okay.
one is about the experiments. What do you think? How much the substrate surface properties or the properties of the fluids that you are using in your system will affect the snap of events that you are seeing? This is about the experiments, and also can you give us a bit of information about the simulation that you use to reproduce the information from the microfluidics? Which kind of method, and how did you implement it?
Okay, for it, actually we conduct the experiment first. Actually, we first get a phase diagram. Actually, at the first time, we want to use the direct numerical simulation to calculate the whole phase diagram. For example, use the open form. However, unfortunately, the calculation is really consuming. Actually, we use for one case, we just choose a very small area and use more than 200 cores in HPC and calculate more than 4 months. So it's really expensive. So we change the research goal. So first we choose a very small tube, for example, the square tube, to research the competition of the mean meniscus flow and the collar flow. This is our first research based on the open form. And then we change the pore throat geometry and to study the geometric criteria. After this critical capillary number and the geometric criteria is got, then we consider to use very simple methods. I think it's very popular, that pore network model. We just input these rows into the dynamic pore network model, and it can be repeat this phase diagram very simply.
Okay, and what about the experiments? How much do you see the effect of substrate surface properties and the properties of fluids that you use in experiments?
Okay, yeah. Actually, in my previous work, I have used some surfactant to change the fluid, so we can change the wettability. But in this work, we focus on the force imbibition, especially for the strong imbibition. So we fix the contact angle to the 10 degree. So that's why we choose water and air, because compared with the water and the oil, water air contact angle is smaller. By the way, we also thermal oxygen the silicon. So we transfer the silicon material to the silica material, because when you heat the silicon material, it will have a very thin film of the silica, so the contact angle can be fixed to the 10 degree.
Okay, thank you very much.
Thank you.
I have a couple of questions myself, Mohammed, if I may.
Yeah, of course.
Okay.
This is very interesting, Wenhai. I think it's your experiments and your work is kind of like in an in-between between like the 2D models where people control things very well and image very easily, right? And the 3D systems that are very hard to control and harder to image as well, but on the other hand, more representative of real systems. So this is kind of like a very interesting in-between zone that you're working on, it seems to me. In this, the model construction, so you had like the pores with depth, right? So is the deeper pores, are they, I'm wondering if like when you have like a water entering, do you have an air pocket above the water or below? Like, is gravity helping the air to be trapped or helping the air to flow out? You understand? If you flip the model upside down, you could have like 100% of air being removed just because gravity would be helping the air is buoyant on water, right? So what's the direction of the...
Okay, actually, and this is a very interesting question. Actually, because our microfluidic chip is very small, the hole size is about 8 millimeter and multiply 6 millimeter, and each pore size varying from 1 micrometer to 200 micrometer. So I think the gravity effect can be ignored in our system. And for our system, because as you know, like for the micro model or microfluidic chip, to get a larger aspect ratio for the deeper, for the depths is to etching the depths for the pores. For the small pores is really difficult. So in our experiment, we just release this confinement. I think generally it's still a tube. So we haven't observed some droplets be trapped in the deeper depths. So you can think it's still a capillary tube. But I think that condition was not happened in our system.
So the pores are not so deep, so you don't really have water flowing under and like leaving a little pocket of air there, right? Because the depth of the pores is not so high, and then gravity effects are not super important. That's what you're saying, right?
Yeah.
Okay. And so you had like this macroscopic capillary number there, right? I didn't quite understand how the alpha, so the ratio between the deepest and like the shallowest pores enter the definition. Is this just by changing the average velocity for a fixed flow rate? How does the alpha enter the definition of the macroscopic capillary number that you used?
Yeah, actually, here we change the capillary number by change the flow rate. Actually, here the lowest capillary number is about 10⁻⁷. For our small microfluidic chips, I think it's the smallest capillary number in the work, because for the microfluidic chips, for this capillary number, we conduct experiments for nearly 1 day. So I think it's very hard to decrease the capillary number in our system. And for the sorry, another question. I forgot your question.
I was just wondering, like, how you had like a definition for macroscopic capillary number, right?
Yeah.
Does the alpha parameter enter that definition?
Okay. Here we give a relationship between the macroscopic capillary number and the microscopic capillary number. For the microscopic capillary number is just defined by the velocity, interfacial tensing, and viscosity. But for the macroscopic capillary number is related to the flow resistance of a whole pulse media. So for the alpha, actually alpha will influence the flow resistance in the microfluidic chips. But when we calculate the flow resistance, we found that this effect is very weak. So we ignored the alpha effect in the macroscopic capillary number definition in that formula. So that's one. Yeah.
Right. And just one more quick question. So you mentioned in one of the slides something about PDMS models. Could this type of technique of like a multi-layers, multi-depths of the model be also used with silicon-based so PDMS microfluidic systems?
Yeah, I think it's okay. For example, for our silicon microfluidic chips, we will we will use a multi-etching first, so we can get a 3D geometry, and then you can just coating the PDMS and then finally you can get a 3D PDMS model. So I think it's very easier to repeat this.
Well, that's very interesting. Super. Thank you very much.
Thank you.
Do I have time for a quick one as well? Or are
Yeah,
we
of course.
moving
Go
on?
ahead. Yeah, definitely.
So I also thought the talk was great. I really enjoyed it. Thanks, Wenhai. And I was curious about what Marcel was pointing out, that you have a sort of 2.5D system, right? Like somewhere in between the 2D and 3D, which is great. So I guess what the leftover 0.5 has that I would think is important is how the connectivity and also the tortuosity of the domain change when you go to 3D.
Yeah.
Right. So my question is, do you agree that this will bring new important effects, or do you think that the kinds of effects that you are seeing now controlling the pore size distribution, for example, are more important?
Yeah, I think so. First, I want to introduce that our study opened a door that we should consider this geometric confinement in the microfluidic chips is very important. For the 3D postmedia, actually, now I'm trying to add more information in the microfluidics. On the one hand, I want to add more information in the microfluidic chips. And on the other hand, I also think that our goal by using the dynamic pore network model to explain this phenomena is very important. So we can input this unique microscopic phenomena into the dynamic pore network model, and then use this dynamic pore network model to explain the 3D postmedia behavior. For example, if you use a rock, you can try to use our improved dynamic pore network model to solve this problem.
Thank you.
We have one last minute question. You mentioned that you added surfactants to change the fluid properties, such as contact angle. Could you please elaborate on this? Which fluid did you use?
Actually, for this experiment, we just use the water and the air. I mentioned I use the surfactant to change the different availability. Is my another work which published in the GFM. So I think if you are interested, you can refer to my paper, because sorry, my English I can't pronounce that surfactant. I think in my paper there have more detailed information about that surfactant. We change the contact angle from the strong imbibition to the strong drainage by change surfactant and combine some complex surfactant and can change the availability.
Okay, thank you very much, Wenhai and Thomas, for these very interesting talks. I enjoyed it a lot, and I'm certain that our audience did too. Now we can wrap up this session. As you are familiar, this was the Porous Media Tea Time Talks team, and recently three of us, Kamal, Nora, and Federico, decided to step down from the team. Kamal was one of our co-founders in this platform. He was instrumental in success of the Porous Media Tea Time Talks. Nora was with us from early on. He joined us from SAC, Student Affairs Committee of Interpol, and she was quite engaged and involved with the PMTTT. And also we had Federico, who helped us a lot. He's done with his PhD, and now he's a postdoctoral researcher at the University of Oslo in Pore Lab. So we thank all three of them for their incredible involvement and support of this webinar series. This is the team right now. It's 8 of us, and we will continue this platform, and we will contribute to the Young Academy in Interpol with more programs, hopefully soon. I have 2 announcements. The first one is that the early bird registration for the Interpol is this Friday, March 15th. So if you want to take advantage of the early bird registration fees, you can register by Friday. And also remember to register for the conference short courses and also side events, especially the Student Affairs Committee events that are designed for you, for PhDs, postdoc, and early career researchers. And this year we have limited seats in those events, so please register as soon as you can. And finally, in the November, there would be an election in Interpol, and we are looking for 4 fantastic teammates in the Student Affairs Committee. So if you are interested in
I think we lost Mohammed here, so but I can take over from him.
colleague, and then yes, and then we can put your name for the election as a candidate. Finally, our next Porous Media Tea Time Talks, it's the special session for Interpol 2024. We will have 2 speakers from the China University of Petroleum, giving 2 diverse talks on various processes. One of them is in hydrocarbon characteristics in nanopores, and the other one is about coupled THMC, thermohydraulic, mechanical, and chemical processes and models for the simulation of shale oil reservoirs. With that, I would like to close up this session. I guess I disconnected for a minute. I'm sorry for that, and thank you all. Have a nice evening, and ciao.
Thank you. Bye.
Thank you very much.